42 is derivative of a quotient, or in other words, quotient rule. So when we do derivatives, we already have the product rule. So when you have two things that are being multiplied, you can't just take derivative, and stick them together. Some of you still like to do that. I'm trying to get you past that hurdle. But the product rule, remember, it's derivative of the first, keep the second. Plus, and then it's keep the first, derivative of the second, right? Okay. So now, we are looking at quotient rule. So quotient obviously refers to a division, so fraction. When you see two things that are being divided, we have to follow this quotient rule. So, right here, at the top, is the general idea of the quotient rule. And what they're trying to say here. F of x refers to the top item. G of x refers to the bottom item. And order does matter here. So it's derivative of the top times the bottom, as is. Minus derivative of the bottom times the top, as is. All over the denominator squared. Okay? So that is our quotient rule. Derivative of the top times the bottom. Minus derivative of the bottom times the top. Over bottom squared. Okay?
It'll always be minus?
Always minus in the quotient rule. Product rule is always plus. Quotient rule is always minus. Okay? Well, and just in general, it's kind of like when you multiply with exponents and divide with exponents. The adding goes with multiplying, the subtracting goes with division. So, okay, so let's try example 1. F of x equals natural log of x over 2x plus 3. They want us to find f prime of x. What you cannot do is say 1 over x over 2, and that's my answer. Okay? You can't just do derivatives of whatever's there. We have to, because it's two things with x being divided, we have to apply the quotient rule. Okay, derivative of the top. 1 over x times the denominator. So times 2x plus 3. Minus, and now flip what you're doing. Derivative of the denominator, 2, times the numerator as is. So times natural log of x. All over, denominator squared. So 2x plus 3, quantity squared. And that is your quotient rule.
Oh, I like it.
Do we need to simplify that though?
We are going to simplify a little bit, and that's where, I mean, how much you simplify it just kind of depends on the problem. Sometimes there's a lot of simplifying that can be done, sometimes not too much. The one thing that is not okay generally to leave is to keep in mind we're not generally supposed to leave fractions within fractions, right? That's generally not accepted, and you won't usually see that. And in this case, I have this 1 over x, right? And if I multiply it into 2x, it would be fine, it'd go away. But if I multiply it into 3, it's not going to go away. To get rid of this x, how do you get rid of a denominator of x? You multiply by x. And so what I'm going to do is I'm going to multiply the numerator by x. If I multiply the numerator by x, you also have to multiply the denominator by x, because whatever you do to the top, you do to the bottom. And this is, I think, the only cleanup step we'll take here. Okay, so at first, we're multiplying everything by x, right? Now, when I say everything, you can kind of distribute this way, too, as we go. 1 over x times 2x. Those x's are going to cancel in that case, right? And then you're left with a 2. So we're also multiplying by x, which makes it 2x. Now, if I do 1 over x times 3, That's going to be 3 over x. Times x means the x's cancel and it's just 3. Minus, we have 2 times ln x, which is just 2 ln x, times x. And I can write that as 2x ln x. The denominator of 2x plus 3 squared, more often than not, you leave it as that 2x plus 3 squared, which I'm going to. And then multiplying by x means I'm just going to put the x out front. So x times 2x plus 3 quantity squared. I'm going to leave it like that. I will say one thing about these is there's lots of different ways to leave them. So not everyone's going to, we're not always going to agree with the book or whatever. There's lots of different ways to leave them. So, questions? Okay, we got 3 more examples to practice the derivative. So using this quotient rule. So example 2, it says find d sub x, so that is another way of saying find the derivative of x cubed minus 2x plus 2 all over sine x.
Somebody found something funny.
Okay, so derivative of the, what do I start with? Top. Derivative of the top. So what's the derivative of the numerator? 3x squared minus 2. So derivative of the top times the denominator. So times sine x. Minus sign. Now it's derivative of the denominator. What's the derivative of sine x? Cosine x. Times the numerator as is. X cubed minus 2x plus 2. All over sine squared x. And I'm going to write it like Wade said it there, sine squared x. The other option would be sine x and put parentheses, and then you're squared outside the parentheses. Do not just write sine x squared without any parentheses. And we could distribute on top. I'm not sure that's going to make it any prettier. Because then you've got sine x and x term, you can distribute that. An option is to separate them. I'm trying to remember, is this where the book starts separating?
Could you start by timesing everything for at least one sine, so you get rid of the first sine and make the other one cotangent?
If you separate it and divide away the sine on
50.
top, then it's 3x squared minus 2 over sine. And then you can subtract the cosine of x cubed minus 2x plus 2 over sine.
Over sine squared x.
Not if you take the cotangent instead.
Oh, and use, okay. Okay, I'd missed the cotangent part there. Yeah, and then we get into, is that any more simplified than what we currently have? Okay, and that's, okay. So I am okay with leaving this one. Okay, we will, not necessarily here today in the notes, but probably when we go over some of the homework, I will show you how the book does some simplifying, how they separate them. And because the idea is that when you separate them, like sine squared x goes under both parts. So in this case, a sine x would cancel. And so you'd have 3x squared minus 2 over just 1 sine x. Over here, and this is where I'm not sure it becomes any more simplified, they were taking cosine over sine, making it cotangent, sine on bottom. Again, I'm going to leave this one, you know. I will even put the comment. There are ways to simplify if, we want to. Okay, so it just kind of depends. So there are ways to simplify that if we want to. I'm opting not to on this one. I didn't figure I'd get much complaints. Excuse me. Okay. Example 3. Let y equal cosine x over e to the x plus x. Find dy dx. Okay, what do I start with?
Derivative of the denominator or numerator.
Okay, derivative of the numerator. So derivative of cosine x?
Negative sine x.
Negative sine x. Derivative of the numerator times the denominator, which is e to the x plus x. Then what? Minus derivative of the denominator. So what's derivative of e to the x plus x? E to the x plus 1. Notice that's more than one term, so you have to have that in parentheses here, yes? So it's derivative of the denominator times the numerator, cosine x. Cosine x could be in parentheses or not in parentheses. Same thing with this negative sine x out front. It could be in parentheses or not in parentheses. All over? Okay, denominator squared. E to the x plus x, quantity squared. And more often than not, we just leave it like that. There's not a lot of times that you actually go farther.
So I'm guessing this last one has like a lot of steps in it, then, since all the other ones have been 1 or 2 steps. Playing devil's advocate.
Are you looking at example 4?
Yeah.
I don't know about log, but we're going to do it. We're using differentials here, so it's a little bit different what we're doing there. But okay, this is another one. We could split it, because you could split it and the first fraction cancel out e to the x plus x. And I think we'll talk about that more when we look at the answer key. But there's not a whole lot that can clean up in these.
I like it.
I mean, right now, I'll be happy if you can just get all the pieces together and remember the process. Now, the difference on example 4, it says find the differential of a dy of y equals x over cosine x. Meaning, when it says find the differential, that means every time we have a term, we have to tag on the differential with it. So if it's an x term, we tag on dx. If it's a y term, we tag on dy. Whatever variable it is, you tag on d whatever when you take the derivatives there. Okay? So, it starts with y equals. What's the derivative of y? One, and then tag on a dy. Right? Derivative of y is 1, tag on dy, and so thus we're finding dy. On the right, we've got a fraction. So, derivative of the numerator. What's the derivative of x? 1 dx times the denominator. So times cosine x, and then we're going to subtract. Nope, we didn't take the derivative of cosine x, so I don't need another dx there. Okay? minus. Now it's derivative of the denominator. So derivative of cosine x is negative sine x. And that's what variable? Dx. So derivative of the denominator times the numerator. So times x. And I'm going to come back and clean that up because that's just kind of ugly the way I currently have it. All over cosine squared x, denominator squared. Okay. As I do just a little bit of cleanup. So 1 dx times cosine x. If I just kind of reorder that, we tend to put dx's at the end. I'm going to say that is cosine x dx. On my next term, minus a negative plus, there's sine x, dx, and there's an x. Where should I put that x? In front of the sine x. So I'm going to say plus x sine x dx. All over cosine squared x. It asks us to find dy. About the only thing I would clean up is in the top. We generally don't tend to leave multiple dx's. We tend to essentially factor it out. So dy is equal to, and I like to factor my dx's out the back. So in parentheses, cosine x plus x sine x times dx all over cosine squared x. The key moving forward, guys, we've got product rule, we've got quotient rule. You can't just take random derivatives. You have to think about, if there's multiple derivatives, how do I make this work? There's no back, right? Right. Okay.
Before the bell. Wow.
We don't have time to talk before.